Hello, in this lecture we will answer on two questions. The first question is to find out the area of the semicircle that is inscribed by a quarter circle. And the second question is to find out the size of this angle theta, of the right triangle ABC. So we'll start with the first question. In the drawing we have a quarter circle. The radius of the quarter circle is equal to 3 units, and inside the quarter circle we have a semicircle. The semicircle is inscribed by the quarter circle, and we want to find out the area of the semicircle. So we will define the center of the semicircle at this point O, and I present to you a new rule, that is rule number 1. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB to this circle, if this tangent AB is tangent to this circle at this point M. Point M is the point of tendency. of tangent AB with this circle. And we also have the radius O is the center of the circle, so OM is the radius of this circle, and as you can see in the drawing, the radius OM is drawn to the point of tendency. That is to say, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then according to rule number 1, the tangent will be perpendicular. The tangent will be perpendicular to that radius. So AB is perpendicular to MO. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So, we'll read rule number 1 again. A tangent to a circle, that is to say, tangent AB, is perpendicular to the radius drawn to its point of tendency. So, AB is perpendicular to MO. Why? Because the radius MO, the radius OM is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, AB is perpendicular to MO, that is to say, this angle is equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so we can actually implement rule number 1 in our drawing. Here we will define this point as point A, this point is point B, we define this point as point C, we define this point as point D, we define this point as point E, this point as point F, and this point as point G. So, and then we will join points O and B together by a straight line. OB is the radius of the semicircle because of the fact that line segment OB starts from the center of the circle, from the center of the semicircle, that is to say from point O, and ends at point B, that is the point on the semicircle itself. Therefore, line segment OB is the radius of the semicircle, so we will define the radius of the semicircle as R. Therefore, OB will be equal to R. So here, the radius OB is drawn to the point of tendency, that is to say it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius, that is to say AC is perpendicular to BO. Again, AC is perpendicular to BO, according to rule number 1. That is to say, this angle will be equal to 90 degrees, and this angle will be equal to 90 degrees, according to rule number 1. Likewise, we will join together points O and D by a straight line. Line segment OD is the radius of the semicircle because of the fact that it starts from the center of the semicircle, that is to say from point O, and then at point D, that is a point on the semicircle itself. Therefore, OD equals to R, it is the radius of the semicircle, and here we have the radius OD of this semicircle that is drawn to the point of tendency. That is to say, it is drawn to point D, that is the point of tendency E with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent CE will be perpendicular to the radius DO. So CE is perpendicular to DO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. And because of the fact that ACE is a quarter circle, C is the center of the quarter circle, I write it down. Point C is the center of the quarter circle. And angle ACE must be equal to 90 degrees. Okay, this angle must be equal to 90 degrees. It's true in any quarter circle that this angle will be always equal to 90 degrees. So actually, in quadrilateral BOCD, we have 1, 2, 3 right angles. Okay, and write it down. In quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 3 times 90 degrees is 270 degrees, plus the size of the fourth angle, that is actually angle BOD, this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we will subtract 270 degrees from this equation, and we will get that the missing angle BOD equals to 360 degrees minus 270 degrees, it is 90 degrees. So we actually found out that the missing angle here, angle BOD, this angle is equal to 90 degrees. Therefore, in quadrilateral BOCD, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we write it down. So we relate to quadrilateral BOCD is a rectangle. I will write it down. Quadrilateral BOCD is a rectangle. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. So I read rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. So actually, here according to rule number 2, the opposite sides of rectangle BOCD, they are equal to each other. That is to say, BO is equal to CD. I repeat again. Side BO equals to side CD in rectangle BOCD according to rule number 2. But we've already found out that BO equals to R, it is the radius of the semicircle. So we can write here that BO equals to R, and from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. CD is also equals to R, so we can write here that CD equals to R. Likewise, according to rule number 2, OD equals to BC. OD equals to BC, according to rule number 2. But OD equals to R. We know that OD equals to R, it is the radius of the semicircle. So from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. BC equals to R. So we can write here that BC equals to R. So actually we found out that all the sides of quadrilateral BOCD are equal to each other, and it has also 4 right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. So I write it down that quadrilateral BOCD is a square. Okay, quadrilateral BOCD is a square. So in the next step we will join points O and C together by a straight line. Line segment OC is the diagonal of square BOCD. And in order to find out the length of diagonal OC of square BOCD, we will implement the Pythagoras theorem on this right green triangle OCD. On the green right triangle OCD, according to the Pythagoras theorem, here PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OC square equals to OD square plus CD square. I repeat again, in the right triangle OCD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OC square equals to OD square plus CD square. So OC square, this is the square of the hypotenuse, equals to OD square. OD equals to R, so OD square is R square plus CD square. CD equals to R, so CD square is R square. So in conclusion, we found out that OC square equals to R square plus R square. R square plus R square is 2R square. We take a root out of this equation and we will get that OC equals to the square root of 2 times R. So therefore we found out that the diagonal of square OBCD equals to square root of 2 times R. Here we can write down that the diagonal OC of square OBCD equals to square root of 2 times R. In the next step, we will extend diagonal CO until it touches the quarter circle at this point. So we extend that diagonal CO by a straight line until it touches the quarter circle at this point, point S. Point S is the touching point of the extended diagonal CO and the quarter circle. So what is the length of the short line segment SO? Here it is very easy to see from the drawing that the length of the short line segment SO, it is equal to CS minus CO. I'll repeat again. The length of the short line segment SO equals to CS minus CO. So SO equals to CS. What is the length of line segment CS. C is the center of the quarter circle. S is the point on the quarter circle itself. And this is exactly the definition of a radius. Any line segment that starts from the center of the quarter circle and ends at point S, that is a point on the quarter circle itself, must be the radius of the quarter circle. And we already know that the radius of the quarter circle equals to 3 units. So, in conclusion, CS equals to 3 units. This is the radius of the quarter circle minus CO. We have already found out that CO is the diagonal of square BOCD, that is to say it is equal to square root of 2 times R. Square root of 2 times R. So, in conclusion, we found out that the length of the short line segment SO equals to 3 minus square root of 2R. Okay, so we can write here that SO equals to 3 minus square root of 2R. In the next step, we will extend the quarter circle to a circle. We will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and in the next step we will extend the diagonal OC of the square by a straight line until it touches the circle at this point, point M. Point M is the touching point of the extended line segment OC in the circle. So what is the length of line segment CM? The length of line segment CM is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle and ends at point M, that is a point on the circle itself. And this is exactly the definition of a radius. Any line segment that starts from the center of the circle and ends at any point on the circle itself is defined as a radius. Therefore, Cm is the radius of the circle, that is to say it is equal to 3 units. So in the next step, I will present to you a new rule that will be rule number 3. according to rule number 3, if chord AB intersects with chord CD at point O, then the following formula is true, that AO times OB equals to CO times OD. I'll repeat again on rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O is the intersection point between the two chords, then the following formula is true, that AO times OB equals to CO times OD. So here, in the drawing, we have here chord AB. This is chord AB. That intersects with chord CD. This is chord CD. And the intersection point is at this point O. Then, so if we have two chords that intersect with each other at point O, then according to rule number 3, AO times OB equals to CO times OD again. If two chords, chord AB and chord CD, intersect with each other at point O is the intersection point, then AO times OB equals to CO times OD. So we actually can implement rule number 3 in our drawing. Because in our drawing, we have chord SM, chord SM, intersects with chord GF at point O. Point O is the intersection point between chord SM and chord GF. I'll repeat again. Chord SM intersects with chord GF at point O. Point O is the intersection point between the two chords. Therefore, according to rule number 3, we get that MO times OS equals to GO times OF. I'll repeat again. MO times OS equals to GO times OF. According to rule number 3. And here, from the drawing, you can see that MO equals to MC plus CO. MO equals to MC plus CO. And we have already found out that OS equals to square root, OS equals to 3 minus square root of 2R. And it is equal to GO. What is the length of line segment GO? O is the center of the semicircle. G is the point of the semicircle itself, and this is exactly the definition of a radius. So OG is the radius of the semicircle, that is to say it is equal to R. And what is the length of line segment OF? For the same reason, OF, it is also the radius of the semicircle, that is the radius of the semicircle, that is to say it is equal to OF. Why? Because O is the center of the semicircle and F is a point on the semicircle itself. Therefore, OF, it is also the radius of the semicircle, that is to say it is equal to R. So, GF equals to R, and OF, it is also equals to R. And R times R is R squared. What is the length of MC? MC equals to 3 units. And we have already found out that CO equals to square root of 2 times R. So in conclusion, MC plus CO equals to 3 plus square root of 2R times 3 minus square root of 2R equals to R squared. Here, this expression 3 plus square root of 2R times 3 minus square root of 2R, it is very similar to the algebraic identity that says that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to 3, A equals to 3, and B equals to square root of 2 times R. So according to this trigonometric identity, A plus B times A minus B equals to A squared minus B squared, the expression 3 plus square root of 2R times 3 minus square root of 2R must be equal to a squared minus b squared, that is to say a is 3, so a squared is 3 squared, that is 9, minus b squared. B is square root of 2r, and square root of 2r squared is 2r squared. Okay, in conclusion, we found out that our expressions 3 plus square root of 2r times 3 minus square root of 2r equals to 9 minus 2r squared. Here it is very easy to see that square root of 2r squared equals to square root of 2 squared, that is 2, times r squared. In conclusion, the expression square root of 2r squared is 2r squared. And this expression equals to r squared. So we will add 2r squared to this equation, and we'll get that 9 equals to 2r squared plus r squared is 3r squared. 9 equals to 3r squared. Here we will divide this equation by 3 and we'll get that r squared equals to 9 over 3. 9 over 3 is 3. So in conclusion, we found out that r squared equals to 3. And what is the area of the semicircle? The area of this semicircle equals to the area of the circle that is actually pi r squared over 2. Okay, so it is equals to pi r squared over 2. It is half the area of the circle. R squared equals to 3, so we will substitute r squared by 3. And we get that the area of the semicircle equals to pi, and r squared is 3 over 2. So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it is equals to 3.71 square units. I repeat again, the area of this semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. In the second method, we will use the things that we have already found out in the first method. So here, this is the center of the semicircle. This is point O. This is point G. This is point F. This is point E. This is point D, and this is point C. This is point A, this is point B. Here we have the square BOCD, and we have already found out that the diagonal of square BOCD CO equals to square root of 2 times R. In the next step, we will join points C and Q together by straight line. Here this equals to R, here equals to R, and OF also equals to R. It is the radius of the semicircle. So in the next step, we will join points C and G together by straight line. Here, line segment GC is the radius of the quarter circle. Why? Because line segment CG starts from the center of the quarter circle, that is to say from point C, and ends at point G, that is a point on the quarter circle itself. And this is exactly the definition of a radius. Any line segment that starts from the center of the quarter circle and ends at any point on the quarter circle itself, it is defined as a radius. So CG is the radius of the quarter circle, that is to say it is equal to 3 units. We join point C and F together by a straight line. Exactly for the same reason, CF will be also equal to the radius of the quarter circle, that is to say, it will be equal to 3 units. I'll repeat again on the explanation, because line segment CF starts from the center of the quarter circle, that is to say from point C, and ends at point F, that is a point on the quarter circle itself. Therefore, CF is the radius of the quarter circle, that is to say it is equal to 3 units. Okay? So I will copy the triangle GCF in a new page, and we will analyze the triangle GCF. So this is triangle CGF that I copied from the original drawing. Triangle CGF, this triangle is an isosceles triangle. Why triangle CGF is an isosceles triangle? Because of the fact that side CF equals to side CG equals to 3 units. It has two sides that are equal to each other, and the base of the isosceles triangle is FG. Here, FG is the base of the isosceles triangle, triangle CFG. And CO is the median to the base. Why CO is the median to the base? Because of the fact that line segment CO divides the base FG into two equal parts. That is to say, FO equals to OG equals to R. Okay? And we have also rule number 4 that is related to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. I'll repeat on rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So actually, according to rule number 4, the median CO to the base FG of the isosceles triangle CFG is perpendicular to the base. So according to rule number 4, CO is perpendicular to FG. So if CO is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle will be also equals to 90 degrees. Okay, the median CO to the base FG is perpendicular to the base FG, so if CO is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So here, in the original drawing, we know that the median CO is perpendicular to the base FG. That is to say, this angle is equal to 90 degrees, and this angle equals to 90 degrees because of the fact that the median CO is perpendicular to the base FG. So actually, we will focus on the right triangle COG, and we will implement the Pythagoras theorem on the right triangle COG, the right triangle COG. Okay? So I will copy the right crane triangle, triangle COG in a new page, and we will implement the Pythagoras theorem of the right crane triangle, triangle COG. So this is the right crane triangle, triangle COG that I copied from the original drawing. According to the Pythagoras theorem, PT is the variation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is CG squared. And it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to CO squared plus OG squared. So CG equals to 3, so CG squared is 3 squared. 3 squared is 9. It is equals to CO squared. CO is square root of 2r, so CO squared will be equal to square root of 2r squared plus OG squared. OG equals to r, so OG squared is r squared. So in conclusion, we found out that 9 equals to square root of 2r squared. Square root of 2r squared is 2r squared plus r squared. So 9 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared. We will divide this equation by 3 and we will get that three r squared over r squared is r squared and 9 over 3 is 3. So we found out that r squared equals to 3 and the area of the semicircle is pi r squared over 2. It is pi, r squared is 3, so we'll substitute r squared by 3 over 2. So the area of the semicircle equals to 3 pi over 2 square units, so in terms of numbers it is equal to 3.71 square units. Okay. The area of this semicircle equals to either 3 pi over 2 square units, or in terms of numbers it is equal to 3.71 square units. We finished with the first question. In the next step I will present to you the second question. In the drawing we have the right triangle, triangle ABC. We know that here we have the right triangle, triangle ABC. We know that side AE equals to side EC, or line segment AE equals to line segment EC. We also know that side BC equals to 6 units. Line segment DE equals to 2 units, and we also know that line segment DE is perpendicular to the hypotenuse AC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees. We know that this angle ABC equals to 90 degrees, and angle BAC is the angle that we are looking for. Angle BAC equals to theta, and we want to find out the size of this angle BAC that is equal to theta. So in order to find out the size of angle theta, we'll do a construction. From point E, we will draw perpendicular on BC. I'll repeat again, from point E, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point E and BC as F. In the next step, we will define this angle ACB as alpha. We know the triangle ABC is a right triangle. This angle equals to 90 degrees. This angle equals to theta. This angle equals to theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in triangle ABC, 280 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. For that reason, this angle must be equal to 90 degrees minus theta. So in conclusion, according to our definition, this angle equals to alpha, and we have already found out that this angle must be equal also to 90 degrees minus theta. Therefore, we can conclude from it that alpha equals to 90 degrees minus theta. Okay. Alpha equals to 90 degrees minus theta. Here we will add to this equation theta, and we will subtract alpha. And we will get that theta equals to 90 degrees minus alpha. Okay. In the right triangle, triangle EFC, this angle equals to 90 degrees. This angle equals to alpha. So this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle, 280 degrees. This angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to theta. So we can write here that 90 degrees minus alpha equals to theta. And what is the size of angle DEF? Angle DEF this angle, you can see it from the drawing, that angle DEF equals to angle DEC, the big angle DEC, minus angle FEC. Okay, it is equal to angle DEC minus angle FEC. Angle DEC minus angle FEC equals to angle DEF. Okay? Angle DEF equals to angle DEC minus angle FEC. So angle DEF, the missing angle, equals to angle DEC. Angle DEC, this angle equals to 90 degrees according to what is given in the question. So we'll substitute angle DEC by 90 degrees. And we have already found out that this angle FEC equals to 90 degrees minus alpha. So we substitute angle FEC by 90 degrees minus alpha. So in conclusion, the missing angle DEF equals to 90 degrees. We will open the brackets here. 90 degrees minus 90 degrees is 0. Minus and minus is plus, so it is plus alpha. So in conclusion, we found out that the missing angle DEF equals to alpha. So this angle DEF equals to alpha. So here in the right triangle DEF, this angle equals to alpha. This angle equals to 90 degrees. So this angle must be equal to 90 degrees minus alpha. Here, this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle DEF 290 degrees. This angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we will substitute this angle 90 degrees minus alpha by theta. Okay, so this angle equals to theta. In the next step, we will prove that the right big triangle ABC is similar to the right small triangle EFC, this right triangle. But first of all, we'll define side DF as X, we'll define side EF as Y, we will define AE as A. If AE equals to A, and we know that AE equals to EC, then EC must be also equal to A. So we will prove that the right big triangle ABC is similar to the right small triangle EFC. So why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to alpha. Okay, so we can write down that angle ABC of triangle ABC is equal to this angle that is actually angle EFC of triangle EFC, and both angles are equal to 90 degrees. I'll repeat again, angle ABC equals to angle EFC, and they are both equal to 90 degrees. In addition, those two angles, they are equal to each other, they are both equal to theta. So angle BAC of triangle ABC equals to angle FEC of triangle EFC, and they are both equal to theta. I'll repeat again, angle BAC equals to angle FEC, and they are both equal to theta. And finally, this angle is a common angle, it belongs to both angles, so we can write down that this angle equals to itself. So angle ACB of triangle ABC is equal to angle ECF of triangle ECF. This is equal to alpha. So this is a common angle that belongs to both triangles. I will repeat again. Angle ACB equals to angle ECF equals to alpha. It is a common angle that belongs to both triangles. So we actually proved that all the angles of triangle ABC, the big triangle ABC, can go to all the angles of triangle ECF. Why? Because those two angles, they are both equal to theta, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, so this angle equals to itself. So we actually proved that all the angles of triangle ABC can go to all the angles of triangle EFC, therefore triangle ABC, the big right triangle, triangle ABC, is similar this is the sign of similar to triangle EFC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC in triangle ABC equals to EF over EC. Of triangle EFC. I'll repeat again. From the fact that triangle ABC is similar to triangle EFC, we will conclude that AB over AC in triangle ABC is equal to F over EC in triangle EFC. So actually, AB over AC. AC is equal to A plus A according to our definition, that is to say AC equals to 2A. So we substitute AC by 2A. And it is equal to EF EF equals to y according to our definition, so we substitute EF by y over AC. EC equals to A according to our definition, so we substitute EC by A. So in conclusion, we found out that according to equation number 1, AB over 2A equals to y over A. Here we have A on both sides of the equation, so A will get cancelled. And we're left only with AB over 2, that is equal to y. So here we will multiply equation number 1 by 2, and we'll get that according to equation number 1, AB equals to 2y. AB equals to 2y. AB equals to 2y, so we can write here that AB equals to 2y. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, this triangle, triangle EDF. So the right big triangle, triangle ABC, is similar to the right small triangle, triangle EDF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ABC of triangle ABC equals to this angle, angle EFD. And they are both equal to 90 degrees. I repeat again, angle ABC equals to angle EFD, and they are both equal to 90 degrees. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So angle ACB, this angle, equals to angle DEF, this angle, and they are both equal to alpha. I will repeat again, angle ACB equals to angle DEF, and they are both equal to alpha, therefore they are equal to each other. And finally, those two angles, they are both equal to theta, therefore they are equal to each other. So angle BAC this angle is equal to angle EDF, and they are both equal to theta. I'll repeat again, angle BAC equals to angle EDF, and they are both equal to theta. So we prove that all the angles of triangle ABC, the big triangle, can go into all the angles of triangle EDF. Right? Both those two angles are equal to theta, therefore they're equal to each other. Both those two angles are equal to 90 degrees, therefore they're equal to each other. And both those two angles are equal to alpha, therefore they're equal to each other. So triangle ABC, the big right triangle ABC, is similar to triangle EDF according to angle similarity rule. I repeat again. Triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that AB over BC in triangle ABC is equal to DF over EF in triangle EDF. I repeat again, from the fact that triangle ABC is similar to triangle EDF, we will conclude that AB over BC equals to DF over EF. AB equals to 2y, so we substitute AB by 2y over BC. BC equals to 6, so we substitute BC by 6. And it is equals to DF. DF equals to x, so we substitute DF by x over EF. EF equals to y, so we substitute EF by y. So in conclusion, we got that 2y over 6 equals to x over y according to equation number 2. Here we will divide both the numerator and the denominator of this side of equation number 2 by 2, and we get that 2y over 2 is y and 6 over 2 is 3. So in conclusion, we found out that y over 3 equals to x over y. We cross multiply this equation number 2, and we get that according to equation number 2, y squared equals to 3x. Y squared equals to 3x. But actually, if we focus on the right triangle EDF, in this right triangle EDF, according to the Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared. I'll repeat again. In the right triangle EDF, according to the Pythagoras theorem, we get that x squared plus y squared equals to 2 squared, that is 4. So now we can substitute y squared in this equation number 3 by 3x, because y squared equals to 3x according to equation number 2. So we get that according to equation number 3, x squared plus y squared is 3x according to equation number 2, equals to 4. So we found out that according to equation number 3, x squared plus 3x equals to 4. Here we will substitute 4 for this equation, equation number 3, and we get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So here we have a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the special formula for x, according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the equation for x, and we find out the value of the values for x. So we get here that x equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c is minus 4, over 2a. 2 is 1, so 2 times 1 is 2. So in conclusion, we found out that x equals to minus 3 plus minus, here we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have only left with 25 over 2. So here x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we actually found out that x1 equals to minus 4. x1 cannot be equal to minus 4 because why? Because x is a length, is the length of side df of the right triangle, triangle EDF. Therefore, it must be a positive number. X is a length, therefore it must be a positive number. It can never be equal to minus 4. Okay. So we cancel this solution, and we left only with the solution, the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. So I will copy the right triangle, triangle DFE in a new page, and we will implement them, but we'll find out the cosine theta of this right triangle. So this is the right triangle DEF that I copied from the original drawing. In this right triangle, triangle DEF, we will get that cosine theta equals to dF over dE. dF equals to x, that is equals to 1, and d equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1/2, it means that theta itself must be equal to 60 degrees. So the answer to the question is the side of angle theta is 60 degrees. It is equal to 60 degrees in its size. Okay? So in the next step I will present to you how to find out the size of this angle, angle theta, according to the second method. In the second method, we will define this angle as angle alpha as we did in the first method. We already know that alpha equals to 90 degrees minus theta from the first method. So I will copy the right triangle, triangle ABC in a new page, and we will implement and we will analyze the right triangle, triangle ABC. We'll define AE as A as we did in the first method. EC will be also equal to A. Therefore, AC, the hypotenuse AC of the right triangle ABC equals to A plus A, that is 2A. So this is the right triangle, triangle ABC that I copied from the original drawing. In the right triangle ABC, here cosine alpha will be equal to BC over AC. So cosine alpha equals to BC, that is 6 units. It is 6 units. It is given as the question. Over AC, AC is 2A according to our definition. So in conclusion, we found out that cosine alpha, according to equation number 1, equals to 6 over 2A. Here we divide both the numerator and the denominator of this side of equation number 1 by 2, and we get that 6 over 2 is 3 and 2 over 2 is 8. So in conclusion, we found out that cosine alpha according to equation number 1 equals to 3 over a. Here we will multiply equation number 1 by a, and then we will divide it by cosine alpha, and we will get that a equals to 3 over cosine alpha according to equation number 1. In the next step, we'll focus on the right triangle DEC, so I will copy the right triangle DEC in a new page, and we'll analyze the right triangle DEC. So this is the right triangle DEC that I copied from the original drawing. In the right triangle DEC, tangents alpha will be equal to DE over EC. DE equals to 2 units, according to what is given as the question, and EC equals to A. So in conclusion, I found out that according to equation number 2, tangents alpha equals to 2 over A but according to equation number 1, we have already found out that A equals to 3 over cosine alpha so now we can substitute A in equation number 2 by 3 over cosine alpha from equation number 1. We'll do it now, and we get that tangents alpha according to equation number 2 equals to 2 over A, but A according to equation number 1 equals to 3 over cosine alpha. So tangents alpha equals to 2 times cosine alpha over 3. Here we substitute tangents alpha by sinus alpha over cosine alpha, and we get that sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. Here we cross multiply this equation number 2, and we get that according to equation number 2, 3 times sinus alpha equals to 2 times cosine square alpha. but we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We'll subtract sine square alpha from this trigonometric identity, and we get that cosine square alpha equals to 1 minus sine square alpha. Now we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha according to this trigonometric identity. So we'll do it now, and we'll get that according to equation number 2, 3 sine alpha equals to 2 times cosine square alpha, but cosine square alpha according to this trigonometric identity equals to 1 minus sine square alpha we'll open the brackets on this side of equation number 2, and we will get that according to equation number 2, 3 times sine alpha equals to 2 times 1 is 2, minus 2 times sine square alpha. Here we will add sine square alpha to this equation number 2, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. Here we subtract 2 from this equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So this is a quadratic equation. In this quadratic equation, the variable that we are looking for is x, so x equals to sinus alpha. The coefficient a equals to 2. The coefficient b equals to 3. And the coefficient c equals to minus 2. And the general equation for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. The variable that we are looking for in our specific quadratic equation is sinus alpha, so here the sinus alpha, we will put the data inside this general formula, and we will find out the value or the values of sinus alpha. X equals to sinus alpha, so sinus alpha equals to minus b, b equals to 3, so minus b equals to minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, times c is minus 2, over 2a. A is 2, so 2 times 2 is 4. So here we get that sinus alpha equals to minus 3 plus minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, 16 plus 9 is 25. So inside the root we left only with 25 over 4. So sinus alpha equals to minus 3 plus minus square root of 25 is 5 over 2. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. It is actually divided by 4, so it is not 2 but 4. 4 minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. But because of the fact that the range of values that sinus alpha can accept, the values are ranging from minus 1 to plus 1. The values that the function can accept, and minus 2 exceeds this range of values that sinus can accept. Therefore, it is incorrect solution. In other words, sinus alpha can never be equal to minus 2 because the values that sinus alpha can accept are ranging from minus 1 to plus 1. Okay, so we cancel the solution and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 half. So if we know that sinus alpha equals to 1 half, and if sinus alpha equals to 1 half, it means that alpha itself equals to 30 degrees. Here we have already found out that alpha equals to 90 degrees minus theta, so we can write here that alpha equals to 90 degrees minus theta. We just right now found out that alpha equals to 30 degrees, so we substitute alpha by 30 degrees and we get that 30 degrees equals to 90 degrees minus theta. We will add theta to this equation and we will subtract 30 degrees and we will get that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that angle theta equals to 60 degrees. Okay, angle theta equals to 60 degrees according to the second method also. We finished the second method, so in the next step I will summarize the lecture. We will start with the first question. In the first question, we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle equals to 3 units, and we want to find out the area of the semicircle. So we define the center of the semicircle as point O. Then I presented to you a new rule number 1. According to rule number 1, a tangent per circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB that is tangent to this circle is point M. So point M is the point of tendency of tangent AB with this circle. And we have the radius OM that is drawn to the point of tendency. That is to say the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. So whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So we can implement rule number 1 in our drawing, because in our drawing we have here the radius OB of the semicircle that is drawn to the point of tendency. That is to say it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AC will be perpendicular to the radius BO. That is to say, so AC is perpendicular to BO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have here the radius OD that is drawn to the point of tendency. That is to say it is drawn to point D, that is the point of tendency of tangent CE with this semicircle, and whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, the tangent CE will be perpendicular to the radius DO. So CE is perpendicular to DO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay, we know that the center of the quarter circle is at point C. Therefore, angle ACE must be equal to 90 degrees. Okay, in any quarter circle, if C is the center of the quarter circle, then angle ACE must be equal to 90 degrees. So in quadrilateral BOCD, we have 1, 2, 3, 1, we have 1, 2, 3 right angles, and the sum of right angles is 270 degrees plus the size of the fourth angle, that is angle BOD. In total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation and we found out that the missing angle BOD equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. So this angle, the missing angle, equals to 90 degrees, it is a right angle. Therefore in quadrilateral BOCD we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral BOCD as a rectangle. Okay, quadrilateral BOCD is a rectangle, and we have rule number 2 that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle BOCD, they are equal to each other, That is to say, according to rule number 2, BO must be equal to BO must be equal to CD. According to rule number 2, that the opposite sides of a rectangle are equal to each other, BO must be equal to CD. But we have already found out that BO equals to R, it is the radius of the semicircle, so we can write here that BO equals to R. So from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. Here CD is also equals to R. Likewise, according to rule number 2, we will get that OD must be equal to BC. OD must be equal to BC according to rule number 2. But we have already found out that OD equals to R. OD equals to R, so from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Okay, BC equals to R. So actually, all the sides of quadrilateral BOCD are equal to each other, they are equal to R. And it has also 4 right angles, therefore quadrilateral BOCD is not a rectangle but a square. Okay, quadrilateral BOCD is a square. We join points O and C together by a straight line. OC is the diagonal of square BOCD. And in order to find out the length of diagonal OC, we will implement the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CO square equals to CD square plus DO square. In the right triangle OCD, OC square equals to OD square plus CD square. So OC square equals to OD square. OD equals to R, so OD square is R square plus CD square. CD equals to R, so CD square is R square. R square plus R square is 2R square, so in conclusion we found out that OC square equals to 2R square. We took a root out of this equation and found out that the diagonal OC of the square equals to square root of 2 times R. Okay, the diagonal OC of square BOCD equals to square root of 2 times R. Then we extended the diagonal CO until it touches the semicircle at point S. And found out the length of the line segment OS. OS, it is very easy to see from the drawing that the length of the short line segment OS equals to CS minus CO. Again, SO equals to CS minus CO. CS is the radius of the quarter circle because of the fact that it starts from the center of the quarter circle and ends at point S, that is the point of the quarter circle itself. This is exactly the definition of a radius. So CS is the radius of the quarter circle, that is to say it is equal to 3 units. CS equals to 3 units, and we already found out that CO equals to square root of 2 times R. So in conclusion, SO equals to 3 minus square root of 2R. The length of the short line segment SO equals to 3 minus square root of 2R. Then we completed the quarter circle, we completed the quarter circle to a circle, and then we extended the line segment, the diagonal OC by straight line until it touches the circle at this point M. And here, what is the length of line segment CM? The length of line segment CM is 3 units because line segment CM starts from the center of the circle, that is to say from point C, and ends at point M, that is the point of the circle itself. And this is exactly the definition of a radius. So CM is the radius of the circle, that is to say it is equal to 3 units because the radius of the quarter circle equals to the radius of the circle. Therefore the radius of the circle will be equal to 3 units. Okay. Then I presented to you rule number 3. According to rule number 3, if chord AB intersects with chord CD in a circle, and the intersection point is at this point, point O, then the following formula is true, that OA times OB equals to CO times OD. So we can implement rule number 3 in our drawing, because in our drawing we have chord SM that intersects with chord GF at point O. Point O is the intersection point of the two chords SM and GF. I'll repeat again, chord SM intersects with chord GF at point O. Therefore, according to rule number 3, MO times OS will be equal to GO times OF. Again, MO times OS equals to GO times OF. According to rule number 3. So MO, from the drawing, it is very easy to see that MO equals to MC plus CO. Again, MO equals to MC plus CO. We have already found out that OS equals to 3 minus square root of 2R. GO equals to R because it starts from the center of the semicircle and ends at point G, that is the point on the semicircle itself. Therefore, GO is the radius, and for the same reason, OF, it is the radius of the semicircle, that is to say it is equal to R. So, GO equals to R, OF equals to R, and R times R is R squared. MC equals to 3 units, it is the radius of the circle, and CO equals to square root of 2 times R. So in conclusion, MC plus CO equals to 3 plus square root of 2R times 3 times 3 minus square root of 2R equals to R squared. This expression is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2 times R. So this, according to this algebraic identity, A plus B times A minus B equals to A squared minus B squared. That is to say, this expression has been equal to A squared minus B squared. A squared is 3 squared, that is 9, minus B squared is square root of 2 squared, that is 2R squared. So in conclusion, we got that this expression equals to 9 minus 2R squared, and it is equal to R squared. We added 2R squared to this equation and we found out that 9 equals to 2R squared plus R squared. 2R squared plus R squared is 3R squared. So in conclusion, we found out that 9 equals to 3R squared. We divided this equation by 3 and we got that R squared, 3R squared over 3 is R squared, and 9 over 3 is 3. So in conclusion, we found out that R squared equals to 3, and the area of the semicircle equals to pi R squared over 2. So we substituted R squared by 3, and we got that pi R squared over 2 equals to 3 pi over 2. So in conclusion, the area of the semicircle equals to 3 pi over 2 square units. So in terms of numbers, it is equal to 4.71 square units. So we finished with the first method. Then I presented to you how to solve this question according to the second method. We use the things that we have already found out in the first method. We know that BOCD is a square and CO is the diagonal of this square, that is equal to square root of 2 times R. GO equals to R and OF also equals to R, that is the radius of the semicircle. Then we join points C and G together by a straight line. CG is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point G, that is the point of the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. For the same reason, CF is also the radius of the quarter circle, that is to say it is equal to 3 units. So then I copied triangle CGF in this new page. First of all, triangle CGF is an isosceles triangle. Why? Because side CF equals to side CG, equals to 3 units. Therefore, triangle CGF is an isosceles triangle. And here, the base of the isosceles triangle is FG, and CO is the median to the base FG. Why? Because it bisects the base FG into two equal parts. FO equals to OG equals to R. And we have rule number 4 that according to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So the median CO to the base FG is perpendicular to the base FG. So CO is perpendicular to FG. If CO is perpendicular to FG, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees, according to rule number 4. Then I copied the right triangle COG in a new page and implemented the Pythagoras theorem in this right green triangle COG. Here we know that CO is the diagonal of the square that is square root of 2 times R. CG is the radius of the quarter circle that is 3 units, and OG is the radius of the semicircle that is equal to R. So according to the Pythagoras theorem, in the right triangle COG, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So CG square equals to OG square plus CO square. CG square equals to CO square plus OG square. CG is 3, so CG square is 3 squared, that is 9. CO is square root of 2R, so CO square is square root of 2R squared, that is 2R squared. And GO is R, so GO square is R squared. So in conclusion, found out that 9 equals to 2R squared plus R squared. 2R squared plus R squared is 3R squared. 9 equals to 3R squared. We divided this equation by 3, and we got that R squared equals to 3. So we know that the area of the semicircle equals to pi R squared over 2. So we substituted R squared by 3. And we got that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first question. Then I presented to you how to solve the second question in 2 different methods. In the first method, here we have the right triangle ABC, side BC equals to 6 units, side DE, line segment DE equals to 2 units. DE is also perpendicular to the hypotenuse AC, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. We want to find out the size of this angle BAC, that is equal to theta. In order to find out the size of angle theta, we made the construction from point E, we drew perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our definition. We defined the touching point of the perpendicular from point E and BC as F. Okay? Then here we define this angle as angle alpha, but this angle equals also to 90 degrees minus theta, because the right triangle ABC, this angle equals 90 degrees, this angle equals to theta, so this angle must be equal to 90 degrees minus theta. Therefore, we can conclude from it that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta. We added theta to this equation and we subtracted alpha, and we found out that theta equals to 90 degrees minus alpha. So what in the right triangle FEC, if this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. Then we found out the size of angle DEF, the size of this angle. The size of this angle equals to the size of angle DEC minus the size of angle FEC. Again, angle DEF equals to angle DEC minus angle FEC. So angle DF equals to angle DEC, that is 90 degrees, minus angle FEC, that is 90 degrees minus alpha. DF equals to 90 degrees and angle FEC equals to 90 degrees minus alpha. We open the brackets here and found out that angle DF equals to 90 degrees minus 90 degrees, that is 0. Minus and minus is plus. So in conclusion, we found out that this angle equals to alpha. Angle DF equals to alpha. So if this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, you can substitute this angle that is equal to 90 degrees minus alpha by theta. We did it and we defined this angle as angle theta. Then we proved that those two, the right triangle ABC is similar to the right triangle FEC. But before that we defined DF as X, EF as Y, AE as A, and EC as A. So why the right triangle ABC is similar to the right triangle FEC? First of all, those two angles are equal to each other, they are both equal to 90 degrees. Those two angles are also equal to each other, they are both equal to theta, and this is a common angle that belongs to both triangles. So actually proved that the right triangle ABC is similar to the right triangle EFC according to angle similarity rule. From the fact that those two right triangles are similar to each other, we conclude that AB over AC equals to EF over AC. Again, AB over AC equals to EF over EC. AB is AB, AC is A plus A is 2A. EF equals to Y according to our definition, and EC equals to A according to our definition. So in conclusion, we found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation number 1, so A will get cancelled, and we left only with AB over 2 that is equal to Y. We multiply this equation by 2, and we got that AB equals to 2Y. So here we can write down that AB equals to 2Y. Then we proved that the right triangle ABC, the right big triangle ABC is similar to the right small triangle DF. Why those two triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to theta. Those two angles are also equal to each other, they are both equal to 90 degrees. And those two angles are also equal to each other, they are both equal to alpha. So we, in conclusion, found out that the right triangle ABC is similar to the right small triangle EDF according to angle similarity rule. From the fact that those two right triangles are similar to each other, we will conclude that AB over BC equals to DF over FE. Okay, AB over BC equals to DF over EF. AB equals to 2Y, BC equals to 6, DF equals to X according to our definition, and EF equals to Y according to our definition. So in conclusion, we found out that 2Y over 6 equals to X over Y. Here we divided both the numerator and the denominator of this side of equation number 2 by 2, and we got that 2Y over 2 is Y, and 6 over 2 is 3. So in conclusion, we found out that Y over 3 equals to X over Y. We cross multiplied this equation number 2, and we found out that Y squared equals to 3X. Then we focus on the right triangle EFC. Here, according to the Pythagoras theorem, in this right triangle, we know that X squared plus Y squared equals to 2 squared. Again, in the right triangle EFD, according to the Pythagoras theorem, X squared plus Y squared equals to 2 squared, that is 4. So we can substitute Y squared in equation number 3 here by 3X, because Y squared equals to 3X according to equation number 2. We did it, and we got that X squared plus y squared, that is 3x, equals to 4. We subtracted 4 from this equation, equation number 3, and we found out that x squared plus 3x minus 4 equals to 0. So we have here a quadratic equation, and then our general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the equation for x, and we found out the value of the values of x. Here x equals to minus b equals to 3, so minus b is minus 3, plus minus b squared. B equals to 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, c is minus 4. Over 2a, a is 1, so 2 times 1 is 2. So here we have x equals to minus 3 plus minus. Inside the root we have minus 4 times minus 4 is plus 16, 16 plus 9 is 25. So inside the root we left only with 25. So we found out that x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution is x equals to minus 3 minus 5, that is minus 8. Minus 8 over 2 is minus 4. So the first solution, x1 equals to minus 4. But because of the fact that x is a length, is the length of side df, it can never be a negative number, it must be a positive number. So we cancel that solution, and we left only in the second solution that x2 equals to minus 3 plus 5 over 2, minus 3 plus 5 is 2, and 2 over 2 is 1. So I copied the right angle DF in this new page, and we found out that cosine theta of this right angle. Here we know that ED equals to 2, it is given as the question. DF equals to 1, according to what we have only just right now found out. So here, cosine theta in the triangle in DF, the right angle in DF, this is the right angle, this angle equals to 90 degrees. So in the right triangle in DF, we will find out that cosine theta equals to df over ed. Cosine theta equals to df over de. df equals to 1. de equals to 2. So in conclusion, we found out that cosine theta equals to 1 half. 1 over 2, this is 1 half. So if cosine theta equals to 1 half, it means that theta itself equals to 60 degrees. So we found out that the missing angle theta, it is equal to 60 degrees. Then we found out the size of angle theta according to the second method. In the second method, we define this angle as alpha. We already found out in the first method that this angle also equals to 90 degrees minus theta, therefore alpha equals to 90 degrees minus theta. Okay? We defined AE as A, EC as A, as we did in the first method. Then we focus on the right triangle ABC. In the right triangle ABC, we know that cosine alpha equals to BC over AC. AC equals to A plus A, that is 2A, and BC equals to 6 units, it is given as the question. So BC is 6 and AC is 2A. Then we divided both the numerator and the denominator on this side of equation number 1 by 2. 6 here, from here, we found out that cosine alpha equals to 6 over 2a. We divided both the numerator and the denominator of this side of the equation by 2, and we found out that 6 over 2 is 3 and 2a over 2 is a. So in conclusion, we found out that cosine alpha equals to 3 over a, according to equation number 1. Then we multiplied this equation by a, and we divided by cosine alpha, and we found out that a equals to 3 over cosine alpha. Then we focus on the right triangle EDF. So I copied the right triangle EDF in a new page. In this right triangle EDF, EC equals to A according to our definition, D equals to 2 according to what is given as the question. So here tangent alpha equals to DE over EC. DE equals to 2, EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over A. But according to equation number 1, we already found out that A equals to 3 over cosine alpha. So we can substitute A in equation number 1 by 3 over cosine alpha. We did it and we got that tangent alpha equals to 2 over A, and A is 3 over cosine alpha. So in conclusion, we found out that tangent alpha equals to 2 times cosine alpha over 3. We substituted tangent alpha by sinus alpha over cosine alpha, and we got that sin alpha over cosine alpha equals to 2 times cosine alpha over 3. We also multiplied this equation, equation number 2, and we found out that 3 times sin alpha equals to 2 times cosine square alpha. Then we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity, and we got that cosine square alpha equals to 1 minus sine square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it, and we got that according to equation number 2, 3 sine alpha equals to 2, and cosine square alpha equals to 1 minus sine square alpha. So here we open the brackets of equation number 2, and we found out that 3 sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We added 2 sine square alpha to this equation, and we found out that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation, equation number 2, and we found out that 2 sine square alpha plus 3 sine square alpha minus 2 equals to 0. So here the missing variable in this quadratic equation is sine alpha, so x equals to sine alpha, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. So the solution for a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific expression, a quadratic equation, the missing variable is x, so x equals to sinus alpha. The missing variable is sinus alpha, so x equals to sinus alpha, and it is equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, so it is minus 4 times 2, c is minus 2, over 2a. A is 2, so 2a is 2 times 2, that is 4. So here we got that sinus alpha equals to minus 3 plus minus. Inside the root we have minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, 16 plus 9 is 25. So inside the root we have only left with 25, so it's sinus alpha equals to minus 3 plus minus square root of 25 over 4. Square root of 25 is 5, so in conclusion we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5, that is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. But because of the fact that the range of values that sinus alpha can accept, they are ranging from minus 1 to plus 1, and minus 2 exceeds this range. That is to say, sinus alpha can never be equal to minus 2, so we cancel this solution, and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 half. So we found out that sinus alpha equals to 1 half. So if sinus alpha equals to 1 half, it means that alpha itself must be equal to 30 degrees. And we have this equation that alpha equals to 90 degrees minus theta. So we write down this equation that alpha equals to 90 degrees minus theta. Then we substituted alpha by 30 degrees, and we got that 30 degrees equals to 90 degrees minus theta. We added theta to this equation, and we subtracted 30 degrees, and we found out that theta equals to 90 degrees minus 30 degrees, that is 60 degrees. So we found out that the missing the missing angle, the angle that we are looking for, that is angle theta, equals to 60 degrees. So in both methods, we found out that the size of angle theta is equal to 60 degrees. Okay, thank you very much.